Hello and welcome to the first video accompanying lecture 28. In this lecture we're going to cover section 13.3 from Young 14th edition. The topic of this single section covered in this lecture is gravitational potential energy. Okay, so that's what we're going to be talking about. Energy in a gravitational field. We have some objectives. We want to understand that gravitational potential energy for universal gravitation is derived from the force equation as for any non-constant force like the spring force. Okay, so we're going to use the general form of the definition of work. All right, and then of course to relate that work to potential energy. The integral definition of work. We want to understand that the convention is to define zero gravitational potential energy for a system at an infinite distance away from the source of the gravitational force. All right, because anytime you have potential energy, you always choose where your 0 point is. And the natural choice here is to set it as 0 at infinity, which might not seem initially like the right choice or the most logical choice, but it certainly is, okay? And we will get used to it. And our third and final objective is to apply gravitational potential energy to situations where mechanical energy is conserved. Okay, so what are we talking about when we talk about gravitational potential energy, right? Because we've talked about that a lot, but now we're talking about what I would say is true gravitational potential energy. It's just sometimes we don't need the true version because we can get away with using the approximate version. Okay, so in many situations on Earth, we say gravitational potential energy is mgh, okay, which is great, that's fine, but this only applies to near the surface of Earth, okay, because we need g to be a constant, which it is for small changes in height, okay? But when h is large, when we're significantly changing our height, say thousands of kilometers, we need a new form of gravitational potential energy because g certainly is not constant. We saw that in the previous section of this chapter. All right? And so we need this new form of gravitational potential energy to incorporate universal gravitation. All right? So we have to derive this new form of gravitational potential energy, again, using the integral definition of work. Okay? So, what is escape velocity? This is something you've probably heard of before. So, a consequence of universal gravitational potential energy, which we're about to derive, is that we can calculate the minimum initial kinetic energy an object needs to escape the gravity of a large body like a planet. Okay? Because we can just set up a conservation of energy equation and solve for V min. Okay? And we can think about what E final must be in that situation. I'll speak to that in just a moment. All right, so let's get down to our key formulas. All right, so I've included the definition of G just because it's a constant we use so much and we're just getting used to it. So I wanted just to repeat it here for quick reference. So you don't have to be flipping back to the previous notes, for example. All right, so here we have our definition of work. This would be a totally general definition of work as the integral of the dot product of F and dr. dr is just our displacement differential. F, of course, is the force, because every force has its own work, so this would have to be the force of gravity since we're talking about the work done by gravity, okay? And of course this is the work done by gravity, right? Not the work done against gravity or anything like that. But what makes it not completely general is that we have some defined limits here. We're specifically going from r to infinity. Well, here, r is the radius, all right? So it's the initial radius, it's starting at the ground. Okay, so we're not starting inside of something, we're starting on the surface of a spherical object. Think a planet, okay? Of course, all this discussion applies best to astronomy, rocket science, basic rocket science, and so on, okay? So it's the circumference of our planet, the radius of our planet. And that's where we're gonna start. And then we're gonna find out how much work gravity does going from R, okay, the ground, to an infinite distance away, right? So that's the work done by gravity when an object is removing itself completely from the gravitational influence of a planet, which of course, based on the expression for the force never goes away, right? It's inversely proportional to 1 over r squared, so it approaches 0 as r approaches infinity, but it does so asymptotically. So it never quite gets there, so truly it has to be infinity, okay? But if you're far enough away, functionally that is infinity, right? If we were in a distant solar system, we would, for all practical measurements, experience no gravitational pull from Earth, right? Just it'd be so infinitesimally small. That would be infinitely far away, right? So when we talk about the work done by gravity, it would be to take an object off the surface of the Earth and move it so far away from Earth that it would never return. Okay? So the dot product, by definition, gives us the scalar multiplication times cosine of the angle between the two vectors, this being the force of gravity vector, this being the displacement vector. Okay? Those two vectors are perpendicular to each other. Right? dr is one way, gravity is the other way. Okay? So 180 degrees is the angle between them. When we take cosine of 180 degrees, we get a negative. All right? All I've done here is just write the force. This is the universal force equation. G m1 m2 over the distance between their centers squared, r squared. Okay? All right? So r squared here is just a variable. Of course, we're going to evaluate it at the lower definite limit of the radius of an object. Okay? So then I do the antiderivative. When I do the antiderivative of this particular power, r to the negative 2, with respect to r, well, I pick up a negative. So that means the negative that we got from the cosine of 180 multiplied by the negative from the antiderivative becomes a positive. Okay? But then we're going to evaluate our limits, right? Because this is the work done by gravity. Well, the work done by gravity, right? We have the final amount being, or the final location being infinitely far away from the source of the gravity. Well, that means that when we evaluate at r equals infinity, what do we get? 0, right? The upper limit is 0, okay? So work final is 0, right? Or I should really say U final is 0, right? Because the work is equal to delta U. So the final potential energy is 0. More on that in just a moment. But the initial one, right, because it's just going to be, we're going to have our evaluation, right? Because we know that work is equal to U delta U. So we'd have U final minus U initial. Well, this means this must be U initial. But look, that's where the negative comes from, because it's evaluated at the upper limit minus evaluated at the lower limit. So we have our negative shuffle, right? We get a negative from cosine of 180, we lose it with the antiderivative, we get it back with the limits of integration. Okay? All right, so here's our final expression of the work done by gravity. It's negative. Okay? Gravity's doing negative work. Now, that is absolutely what we need, because we are working against gravity. The displacement is literally anti-parallel at 180 degrees to the direction of gravitational force, so it better be doing negative work. But here's the part that gets interesting. Remember, we defined U final as being at r equals infinity. So that means that our U initial is negative. Okay? Our U initial is negative G m1 m2, or big M little m over r. All right? And just quick thing, do notice that the force is inversely proportional to r squared. The work and gravitational potential energy is inversely proportional to just the length, the radius. Okay? So squared inverse proportionality, just straight up inverse proportionality. All right? Good thing to take note of, maybe, because I'm focusing on exactly explaining how this all works, but that's one of the things you want to look for and not mix up. Okay? So, as I was saying, the very interesting result of this particular choice of U final being 0, okay, is that the potential energy, right, that your kind of instantaneous potential energy, your initial potential energy, is equal to the work done by gravity. Okay? So actually, instead of, because we're used to the difference being equal to the negative. So the change of potential energy is equal to the negative of the work that created it. It doesn't have to be just gravity, right? This is a general statement. Just the subscripts have to be the same. Okay? Apply to a spring force, for example. Now, that's fine, but unlike the spring force, the final potential energy is 0, not some stored amount of energy. So instead of storing energy, it's going away. So we often thought about potential energy as being at the top of a roller coaster, or being at the bottom of a fully compressed spring or something. So that was that idea of storing it. It's ready to be released. You're going to roll down the roller coaster, or you're going to fling up in the air when the spring releases. Okay? Turning that potential energy into kinetic energy. But we have a new convention here. We have a new idea. This is a new one. Now, what does it mean? It means that what gravitational potential energy represents is being at the bottom of a potential energy well. When you're at the surface of Earth, when you're standing at the surface of Earth, you're at the bottom of that well. You have a negative gravitational potential energy because you're trapped. You have to expend kinetic energy if you want to be free of the gravitational well you find yourself in. Of course, don't get me wrong, it's a life-nurturing gravitational well with liquid water and an atmosphere. But we're trapped at the bottom of it, energetically speaking. Now, if you think about it that way, the signs make sense, the sign convention, because you've got negative potential energy as your initial potential energy, and you've got that gravity does negative work if you want to get out of that well. Because gravity is going to work against you the whole way if you climb up out of the well. And you do that, of course, again, with kinetic energy. Well, that's a good segue, right? How do you get out of the well? Well, one way would be to have a final energy of zero. So let's say you expend just enough energy, positive energy, to equal in magnitude the negative gravitational potential energy you started with, the well that you were in, right? So you spent just enough energy to roll up the side, right? Roll up the side of that potential energy well with kinetic energy, and you got up the side and you got out, okay? No excess. So in that ideal case, your total final energy, because this is the total, is zero. You neither have gravitational potential or kinetic. Truly zero energy. Because you're at rest infinitely far away from Earth. And there's no other sources of gravity out there, right? You're at rest infinitely far away from that one source of gravitational potential energy. Okay? Now you can, of course, include more planets and complicate the problem, right? So that's the idea. That's the minimum, right? In practicality, you would probably be a little bit greater than the minimum, but that's the idea. And so then your initial total energy to pull off a final total energy of zero has to be some amount of kinetic energy in the form of 1/2 mv squared plus your initial gravitational potential energy, which of course is negative because you're in a well. So when you solve for v, since this is just set equal to 0, you can just move things over and very quickly solve for v, you get a value of velocity that is easy to calculate and exactly tells you how fast you have to be going to escape a world of a particular mass and particular radius. Just tell you something of mass density, right? Because it's like, how much mass can you have being some distance away from the center? Okay? All right. So hopefully that all makes sense. I think it's quite interesting. I'm going to do one example to wrap up this video, and then in the second video, I'll do some larger examples. All right, let's do a simple one. All right, so example 2, I'm leaving example 1 for you, just a straightforward calculation. I want to make sure that you understand, you can see the number for yourself of being in a gravitational well. All right, so calculate the change, or I think you should say calculate, not calculating. Calculate the change of potential energy to go up 8,800 meters using gravitational potential energy, MGH. And then using the new form of gravitational potential energy presented in this chapter, okay? There we go, I'm saying that, okay? They give different values, right? They should, they're not going to be in agreement with each other. What is the percent error between the two values? If we go up 8,800 meters, so 8.8 kilometers. So 8.8 kilometers, that's like Mount Everest, okay? So it's like going up from sea level to Mount Everest. And in that case, we would assume that there's no significant change in gravitational acceleration. So then, whatever energy we calculate to go up that high, that should be right? Or what about the energy that pilots need to know in order to get up to cruising altitude, which would be more. That would be like 40 kilometers, so 40,000 meters. So, I'm thinking 40,000 feet. But anyway, however many kilometers it is. So, point being, should we expect a big percent error? I don't think so. Let's see. Okay, so these are just the values we're using: gravitational constant, radius of the Earth, mass of the Earth. Okay, I don't state them here. I probably should have, and I try to always put them in the body of the problem. But it's on Earth. That's Earth's radius and so on. Okay, we're going to use this percent difference formula. So we'll have the potential energy calculated the old way, the assumption way, MGH. The new way, the more accurate way, divided by the more accurate way. Because if you're doing a percent difference, you always divide by the better theory, all right, or the true value. Multiply it by 100, of course, you get percent. All right, so this is the form, right? So U old is just, the traditional way, it's just MGH. Here's the new change in potential energy. This looks a little different than what I just showed on the key formulas, right? Well, that's because this is truly a delta U that we're looking at here, okay? And in this case, U final isn't 0. I'm not interested in escaping. So U final is just this, all right? And since it's delta U, it's U initial, U final minus U initial. Well, they're both negative, so there's a leading negative, okay? And so, that's why sometimes the form looks a little backwards, like maybe because sometimes we can reorder them by distributing, because in this case I left the U final minus U initial. I think I like to do that because I think it's more intuitive. Like you look at that fraction right there and you clearly say, oh, well, that applies to the final location. That's the final potential energy, right? Because it's the radius of the Earth, radius of the Earth plus some extra height, right? And this is the initial potential energy, great. But what a lot of people do is they'll distribute the negative n, and that means that the 1 over RE will be the leading term. Right? So don't be surprised if you see that negative distributed in. So that really shows you that instead you're having U initial minus U final, which sure seems backwards, but it's fine just because we just distribute the negative. Okay. But anyway, so then we're going to have, and this is just the same expression down in the denominator. Now, when we plug in the values, it ends up being 1.17%. Okay. And this is again it's really just dependent on the mass of Earth, the radius of Earth, and how high we're going. Okay. So great. That works out nicely. And is it a large percent error? Yeah, it's actually pretty significant. 1% error is not tiny. You might not measure it, you might, right? So, okay, so you kind of miscalculate how much energy it takes to get up to that height. Because it would actually take less, right? You get that, right? That this is the overestimate. You'd be overestimating the classical way by, the traditional ultra-classical way, because this is all classical mechanics. By 1.1%, you'd be overestimating. Okay, so then I asked here, what is the minimum altitude gain that would cause a 10% error between the two values? Okay, so here I set it up equal to 10, and then I solve for h, okay, which is a bit of a bear, right? But you can just do the algebra. And when you do, you get 5.64 times 10 to the 5 kilometers, or 564 kilometers. So a lot more than 8.8, right? Because that's what this was, of course, was 8.8 kilometers. Yeah, so it's a lot more. And in fact, pretty darn high, right? That's 564 kilometers. That's greater than the cruising altitude of the International Space Station at about 350 kilometers. So yeah, I guess in those cases, it's it's kind of interesting, right? That even then you could get a real rough estimate if you just want 90% accuracy, by not even taking into account the fact that a satellite is so high, right? But of course, they do call that low Earth orbit for a reason. So you have to be about 0.09, so about 10% of the Earth's radius in order to get that 10% error. Right? It's not exact, right? It's 9%, and it gets you 10%. So don't think it's the exact relationship, but it ends up being kind of a rule of thumb. Now, it's a nonlinear relationship, so they're not always going to be, it's not going to be like 29 for 30 and so on. But at this particular point, you get increase your height by about 9%, and your error is about 10%. Anyway, this is going to wrap up the first video. So please check out the second video accompanying lecture 28, where I'll do 3 more examples. Thank you for watching.